So our session do not formally start until 1 o'clock. That doesn't mean that I'm asking you to leave. What does mean that I'm standing here so that you can ask me any questions on heterogeneous integration in terms of how we are organized? What are the questions that you have that you are wondering about? What is this heterogeneous integration business? What does it do? And most important, how does that help you in the work that you are doing today? What does it help you to think about what your profession will be like in the future? How do we all together help our profession, help the work that we are doing today? We have scheduled, if you look at the agenda, we have scheduled from 1 o'clock to 3:30, all presentations, and then we have a roundtable discussion. At that time, you can most likely interested in asking technical questions, not necessarily in the area of the heterogeneous integration roadmap. How are we set up? What do we do? Two different kinds of things. So I have a set of business cards that if you have more questions later on, you want to contact me, I have a business card over here. So if you like to pick one up. So I will be speaking from 1 o'clock to 1:20. Actually, I think the presentation that I have prepared is probably going to be a little longer than this. And so everybody will be pushing a little bit later on. We do have a keynote speaker. You may have heard his name mentioned earlier. He appeared. His name is Shalf. John is at Lawrence Berkeley National Lab. He is a person whose main interest is in supercomputing. And why does supercomputing have to do with heterogeneous integration? Isn't that an important question? What does supercomputing have to do with heterogeneous integration? Of course, if you heard about the supercomputing and you look at how do we rank the fastest supercomputer in the world, you will find out that on May 31st this year, the announcement of the fastest supercomputer is the supercomputer at the Oak Ridge National Lab. Before that, the fastest supercomputer for 2 years was the Fukuoka supercomputer designed by Fujitsu in Japan. They hold that record for 2 years. And then this year, the Oak Ridge National Lab took over. The Oak Ridge National Lab, the supercomputer, is powered by the AMD processors. AMD chiplets. AMD chiplets on organic substrates that we talked about in earlier sessions, some of you at the earlier sessions. Yeah, thank you. So John is very much interested in supercomputing. He will be the chair of the supercomputer conference in Hamburg next year. And but he has always been very interested, but more important, he's always interested what goes in to make the supercomputer to be what it is to be. For many, many years, the supercomputers are always designed specifically to be a supercomputer. Do not take commercial products and put it in. But this supercomputer at Oak Ridge National Lab is the AMD chiplets. And the next one that is coming up, oh, I forgot to mention, yes. The supercomputers in the Oak Ridge National Lab, not only that it win the #1 in terms of exascale, but also it is #2 to be the most sustainable, the green supercomputer, in terms of the fact that powerful performance is the most efficient. Okay, the next one. The next supercomputer that's going to come up also in the same idea that the Department of Energy has, is to use the commercially available processors to put into the supercomputer. So the next one that is going to come up will be the Aurora supercomputer at the Argonne National Lab. It is being produced together, and that one comes from the Intel chiplets. You could see that in some ways it's very interesting that the Department of Energy has decided to use the commercially available processors to power the supercomputers. It's a very, very interesting concept in the sense that what you want to do is not only to help the industry, but in today, the best and the fastest industry is not necessarily a custom product, but it's a commercial product that's successful in the marketplace. It's a changing concept that we have. I shouldn't say we have. I think the Department of Energy have to see that how the commercially product now becomes the most competitive product in terms of performance, in terms of energy. So I gave John we especially invite John because we think it's an important thing for us to have, because we recognize that chiplets is going into the very, very top high end of the performance. So also with what we have is that we have featured some of the presenters. We have data centers, Kanad. Many of you, all of you knows him. right? Who do not know Kanad? Okay, he is the professor. He's a professor here, but also important. Did you tour his lab yesterday? I think you taught his lab, right? I mean, what he is working on for years and years is thinking about how to make data centers efficient. Then we have aerospace and defense. Then Blass, Lockheed Martin, just down the street from us in Owego. For many years, the very important industry in this area. And then it's the co-chair for the aerospace and defense. That's another area that takes the leading edge. DARPA has been leading the microelectronics resurgence for years. And so aerospace and defense is the first industry that adopt the idea of the chiplets, the idea of heterogeneous integration through the DARPA program. Then we have MEMS and sensor integration. MEMS and sensors are tremendously important for us, not only in the sense of getting edge. They are the technical working group that take the data from the edge and move into the center. So now we are looking at how do we do that? How they are doing that. So in terms of heterogeneous integration, in terms of how whole microelectronic industry, the MEMS and sensors are at the forefront of getting the physical data and then move them into the data that we are thinking about in terms of the digital transformation. And Shafi, of course, is a distinguished product of this university. Is that right? I shouldn't say distinguished product, right? So medical, health, and wearables, Mark Poliks. Mark, of course, is a distinguished professor here, and but he is also pioneering a new area of wearables, health, and then finally single or multi-chip integration. And Annette, are you going to present? Okay, great. So no. I forgot all about it. I just dawned on me that someone needs to present this. Thank you. So Annette is the co-chair for the single multi-chip integration. And in fact, if some of you remember the ITRS, what single multi-chip integration chapter is modeled upon the original chapter in the ITRS packaging chapter. Bill Bottoms and I worked on that chapter for years and years, and then we ported over, and that is right now the single multi-chip chapter. In which, what does that chapter say? Is if you want to understand the flow of just from design to finishing and product, you see it there. If you want to understand what is the knowledge flow, you will see it in there. And we just nurtured a reliability section in there, and then we spin it off. Now we have a new reliability chapter. So that is an area that we think about how to start new chapters. Okay, is that time for us to start? Okay. How do I move forward, please? Okay. So just forward. So I can just forward. This is my first page. So John is already there. I see him. So I'm still here. Okay. Yeah.
Anyone know how to run this thing from a browser? PDF file.
No, this is not the PDF file.
It is.
So no, I can change it to the house. No.
Not from a browser. Control if you use it is I already did it.
So this is not a PowerPoint?
No.
So why not just,
Do you have the
of course, I gave you the PowerPoint somehow. I'm sorry. I'm sorry. We have totally, I'm
I know,
sorry.
but it won't open because it's not installed.
Yes, I can see that this is not PowerPoint.
Look at that.
Okay. Wonderful.
All right, so you should be able to use that.
So. Okay. So we're today, heterogeneous integration, paving the way for microelectronics resurgence. And I particularly choose this cover because it is the first image from the NASA's new Webb telescope, looking into the future. That's what we do in our roadmap, looking into the future. So agenda. We first talk about that this is no ordinary times. Then we talk about the transistor's 75th anniversary. Talk about the roadmap and innovations in the microelectronic resurgence. Then I will quickly summarize. No ordinary times. The world is going through climate change, war in Russian invasion of Ukraine, other geopolitical conflict. For economy, we are seeing inflation and of course, COVID-19. On the other hand, we are seeing a resurgence of the electronic systems powered by semiconductor microelectronics technology renaissance. In US, the subsidies, the money from the CHIPS Act spark significant investments in new fabs and packaging facilities. We have TSMC, new fabs, Intel, Global Foundries, Texas Instrument, Samsung Micron. Benson gave me a link to I think quite a new link, right? A couple days ago, that showed that we are talking about these collectively. We are talking about $200 billion in the next 10 years. And within that, there is the Intel packaging fab in New Mexico. There is the Samsung has announced a new fab, but did not say the location as yet. I think they are trying to see, no, I'm going to say differently. I have given that information to Bagan and see whether he can bring it over here. And so tremendous investment going to happen of the fabs in US. And same thing is happening in Europe, in Japan, in Taiwan, India. India want to attract fabs into India. Singapore already announced the GlobalFoundries investment, and Malaysia, Vietnam, and so on. So what I'm trying to say is that there is a surge of investment in fabs, in microelectronics, in packaging, with the recognition that semiconductors and microelectronics is in the foundation pillar of many, many industry around the world. It's not US, it's not Europe, but totally around the world. Everybody is interested in recognizing the importance of this. And we see also in looking at those fabs, you ask yourself, who is using all those chips? It's not all of them the most advanced nodes. Some of the fabs very clearly said that they are making products from the more mature nodes, because we recognize that there is a whole spectrum of products that need to be made. So this is really no ordinary times. This is the time that we have to recognize that there is a surge of interest, surge of investment in semiconductors, in microelectronics, in packaging, and very importantly, in heterogeneous. So this is the 75th years of transistor. So December 16th, 1947, 3 people. They came there in Bell Lab in New Jersey. 3 hours drive from here. And they demonstrated the first working transistor known as a pound contact. And William Shockley invited the junction transistor in February of 1948. This is the first stone in the foundation of our smart, intelligent society. The Nobel Prize in Physics was awarded to these 3 people. William Bradford Shockley, John Bardeen, and Walter Hauser Brenton for their research on the semiconductor and the discovery of the transistor effect. Not too long after that was the invention of the transistors of the integrated circuit independently by Jack Kilby and Robert Noyce, 1958 and 1959. With that, it started the 50+ years of scientific and technology progress by scientists and technologists around the world. And I use the word today in service of humanity. Think about all the things that the semiconductors, all the things that integrated circuits, all the things that electronics does for us that we are enjoying today. So, Moore's law. If you look at the left, you will see that this is the page from the paper that is now what we call Moore's law. It's a paper published in 1965 and not very long, page 104 to 107, April 19. And if you look at the, if you have looked at this one, this is the Moore's law that we know today. It says that we double every 2 years. But I want to take you to the attention of this one, this cartoon over here. At that time of the Moore's law, 100% of the product goes into military sector, and but Dr. Moore is already thinking that it could be that electronics could be sold in department store next to cosmetics. His vision is that he wants to get out of that one. 1965. And then in the paper, there is a section of he said, day of reckoning. He said, it may prove to be more economical to build large systems out of small functions, which are separately packaged and interconnected. And that's what he projected. He aspired that in the future, the electronic systems, whether we are talking about supercomputers or whether we are talking about edge computing or other things, that we could build the system out of smaller functions which are separately packaged and interconnected. So that's, to us, it's a statement of heterogeneous integration through chiplets and SIP. So heterogeneous integration roadmap, sponsored by Electronic Packaging Society, SEMI, Electronic Devices Society, IEEE Photonics Society, and ASME Electronics and Photonics Packaging Division. And we cover the entire microelectronics technology ecosystem. We have members from industry, academia, and government organizations. What do? We articulate the state of art of advances of technology and science, talk about the future directions, what are the significant roadblocks, and what are the potential solutions. So then, because of understanding this, then we have scientists and technologists work in universities, work in industry, work in research institutes, so that they can pave the way into the paving the way for the future. the 2020, we've released the first roadmap October the 10th, and then we have 2020 update, 2021 update, and 2022 revision are in place. If you go to the Electronics Packaging Society and find the roadmap section, you will see we have a statement in there on how we are organized, what is the, how do you join to work on the roadmap, and all the information on the system are in place. And also you can download the original chapter and other information. So this roadmap is a roadmap that is driven by the microelectronic systems products, and so we want to show first that on the top left you see that there are 6 market applications, 6 system and market applications, start from high performance computing, mobile, medical health and wearables, automotive, IoT, aerospace and defense. Then you have these market applications, then you will say, how do we make them happen? So that is the heterogeneous integration components. We have these 5 working groups, start from single chip and multi-chip integration, integrated photonics, integrated power, MEMS and sensor integration, 5G communication, and beyond. These are what we will call component, heterogeneous integration components. Then there are the cross-cutting topics, materials and emerging materials. Just like in this symposium, I heard a lot of very important talk on materials and on new materials that is coming forth. Then we have emergent research devices, test, supply chain, security. Security is dealing with cybersecurity and thermal management. Then we have a new chapter formed last year, which is reliability. Then integration processes will be SIP, module, 3D and 2D, and interconnect, and wafer level packaging. Wafer level packaging, we talked about fan in and fan out, and actually with wafer level packaging, we also include panel level. Perhaps the most important part I leave to the last. That is, all systems start with design. So we have co-design and simulation, two separate but closely connected chapters. Well, I mentioned the names, but I want to show who they are. The roadmap comes from people. So I would like to just show you some of the people in the roadmap chapters. So test, we have a new leadership. So Dale Armstrong and Ken Lanier. Now we have Ken Butler and George Hotade. In the supply chain, Tom Salmon, Sammy retired. And so we have Paul Trio, Kitty Purcell, and Seva Savasky. And in automotive, Ume Ray and Rich Rice. Ume ran out working with Animi, and Rich Rice retired. And so we have two new members leading chair and co-chair of the Automotive Technical Working Group. Well, Kanad is wearing a mask, but he actually looked like this. Thank you. So we have HPC and data centers. Then we have thermal and 2D and 3D interconnect. and integrated photonics. Test, you saw the new person we talked about, and then we have co-design. Real live people, each of them leading their team, and they have working with them. Some groups are very large, some groups are small. We counted approximately, we have about between 350 to 400 people working on it, not just in the US, not just in Europe, but Asia and everywhere. Approximately about 60% are from industry, about 30% are from academia, and the rest are research institute and government. So we show you 5G, and Tim Lee leads 5G and also aerospace and defense. Benson and me are in the mobile wafer level packaging. Rosalia Bianca, she has been in Shanghai, but she will be returning to US in the next couple of months. I'm not sure whether she will be returning to US or returning to Europe. ATS is in Europe. And then emerging research devices and cybersecurity. Actually, if you look, some of the people are in this room. And where's Chen? Okay, yes. So, so these are the technical chairs and co-chair in medical health and wearables, emerging research devices, IoT, reliability, modeling simulation. And you could see IoT is Robert Lowe in Taiwan. Automotive, SIP and module, and MEMS and sensor, Shafi is right here, supply chain, and integrated power electronics. Doug is here, and also I could see Bob Connors here, and then single multi-chip, and that is right here. I mentioned the fact that the different societies. I mentioned that, but the supply chain is very important, and SEMI represents the companies around the world in the electronic supply chain. If you start from the outside, you could see that these are the companies such as in electronic systems, such as IBM and Google. And then you work one step in, you have the fab people and also the design people, companies such as AMD and TSMC. And then we have the OSATs such as ASE, JSET, and go all the way back in. So SEMI is very extremely important for us because they represent the world's major companies in our electronic systems. Looking ahead, our business, you could see that we are projecting a compound annual growth rate of 5.7%, and the total electronics semiconductor market will grow almost 1.8 from 2019 to 2026, fueled by servers and storage, communication infrastructure, mobile phones, tablets, and etc. Driven by advanced node silicon and desegregation of the chip architecture. This is system focus. So we talked about the heterogeneous integration roadmap. We have these 6 areas, which are the market system drivers. And I put here the definition of heterogeneous integration. From ITRS, we were transistor focused, and now we are system focused. This is my very favorite cartoon from Dr. Philip Wang at Stanford. And his point is that during Moore's law time, the single focus is miniaturization to go to the next node. But now we emerge from the miniaturization tunnel. The opportunities for research, opportunities for innovation is becoming infinitely bigger and infinitely open and infinitely wider possibility. Here's a slide from DARPA that heterogeneous integration is the fourth wave in materials diversity, functional diversity, and technology diversity. The last one on technology diversity is the aspects of the chiplets. So chiplets heterogeneous integration, you might look at it from the point of view of a monolithic SoC and modularize them and then put them in either large MCMs, 2.5D, fan out, RDL, and with bridge, and then 3D. It's a very simplistic, but it's a good way to see how advanced packaging and heterogeneous integration can add value to the out product of our electronic systems. So the AMD's chiplet strategy. Thank you, John, for the slide. And this is a slide in one of his presentations that show how the monolithic 32-core chips can be separately packaged and put into the chiplet format. And then he saved on cost. He showed that originally, if the cost was 1, right now the cost is 0.59. But also, very important is that with that approach, the AMD can develop a whole family of products in one single development in the chiplet format. This is the keynote talk at the Hot Chip 34 conference. You see on the top, your top right, the Intel CEO, Pat Gelsinger, presented. In 1 hour, he covered a whole complete vision of semiconductor runs the world, a complete vision of the Intel future strategy. And he asserted the Moore's law is alive and well. He articulated his vision for Intel and the crucial new role of packaging in continuing this Moore's law into the future. He particularly highlighted the Intel's packaging innovation portfolio. How does he apply to chiplets in the Intel component products, and including power delivery. He specifically talked about power delivery, that is the power come up from the backside and the signals on the top. That would change the whole revolution for us to think about how do we package it. And then he concluded his talk by the message that the Intel community is the steward of Moore's law at this golden age of semiconductors. And I particularly want to show you, he said in this screenshot that I took of his talk, that said, quoted Moore's law, saying is that day of reckoning, it may prove to be more economical to build large systems out of small functions which are separately packaged and interconnected. What does day of reckoning mean? Day of reckoning, from my reading of the dictionary, it says that the day of reckoning means that time is up. Time is up for the classical Moore's law. And we have to find a new way, and this is a new way. So this is the Intel Ponte Vecchio chiplet product that will, as I mentioned, that will be going into the DOE Aurora supercomputer. Really important, use everything that Intel has in their packaging portfolio. You could see that they are using EMIB tile. It's a multi-tile package. You could see that they're using Fibers, which is stacking. And of course, that is not described over here, is that the thermal management is a key aspect, and the use of low temperature solder is very important for them to be able to maintain the warpage. So I show here on the left, the Frontier Oak Ridge National Labs supercomputer, the power by AMD. That is I picked up from the Oak Ridge press release. And then on the bottom, I show the Ponte Vecchio. What I didn't show over here is this one over here. I mentioned to you about Fugoku. That one is the built on the TSMC's silicon interposer technology. Built on the CoWoS silicon interposer. So that is the forerunner of the chiplets technology that we are talking about. You can see that picture right here. So I use this slide to say that in the heterogeneous integration, we talked about what are the research that need to be done. And this one that Madhu Iyengar very nicely lists out those areas that research should be done on thermal management in one single slide. I love it because he really did a wonderful way of expressing on how research need to be done for going forward into the future. So I'll conclude by saying is that we have global recognition that the critical role of semiconductors and microelectronics is the foundation pillar for our economy. So pre-competitive technology roadmap to talk about what are the future visions, difficult challenges, potential solutions, how do we collaborate together to address those. We have this unique opportunity today. I think once in a lifetime today, that all of the investments are going in, and at the same time, all these difficult challenges are there. And we use our roadmap to help our community to identify the directions and to collaborate, work together in advancing the science, technology, and understanding how collaboratively we can work together. Okay, thank you very much. I think I would like to invite John. I have, believe, exceeded my time. Okay. Okay.
Okay.
Okay, John.
All right. Thanks. Thanks, Bill. Let me share my screen here.
Well, John, Benson said I need to introduce you, but I
Oh.
think actually you don't need to. I have introduced you already. What I remember, one thing that I want to introduce you for is that 10 years ago, you were elected to be the rock star of high-performance computing.
Thanks. Yeah, I couldn't quite hear, so should I start?
Okay, you go ahead.
Oh, okay. Great, thanks. So I'll this will basically start off. I think that Bill already covered some of this, but I'll go ahead and jump into it. So I was involved in the DARPA DOE Exascale Grand Challenges report. I was actually peripherally involved in the hardware report, but was in the software Grand Challenges. But you know, the conclusion of all of our reports, 2008 and the companion report that I was involved in 2009, was the primary challenge for getting to exascale computing will be the energy consumption. And most of that energy is attributed to the cost of data movement. The projections we made, technology projections we did in 2009 for a 2016 exascale target ranged from 67 to 200 megawatts, depending on what technology assumptions that we made. But the target for the DOE's $3.6 billion exascale computing project, the ECP, was to achieve exascale in consuming less than 20 megawatts. So we finally got the OLCF, Oak Ridge National Laboratory Frontier supercomputing system, finally hit that mark of 10 to the 18th power operations per second running the LinPack benchmark. This was powered by AMD's Trento 64 processor that was co-integrated, co-packaged with 4 MI250 GPUs. So that's a total of 9,000 CPUs, 37,000 GPUs, and about 8 million cores interlinked together with 145 kilometers of networking cables. So it was #1 in the top 500, but it was also #1 on the Green 500 list at 21 megawatts, and that is no coincidence. Because like we said in 2009, it was power is the ultimate limitation for performance. And if you look at, you know, as Bill mentioned before, you know, advanced packaging, in particular, this chiplets technology is central to both the AMD approach and solution for exascale and the forthcoming ALCF Aurora. Very intense advanced packaging technology was absolutely crucial for co-packaging and reducing the amount of data movement by increasing integration within the package. But now we need to look beyond exascale. So we finally achieved this really momentous milestone. What we're seeing though now in technology trends, this is the diagram that we used from Kunle, Lance, and Herb Sutter to show that the end basically of Dennard scaling. When we couldn't reduce supply voltages anymore, then suddenly the heat thermal loads started going way up, and eventually it came to the point that we couldn't remove more heat from the package. So clock frequencies stalled, single thread performance stalled. So we switched to doubling the number of cores each generation. And we had Moore's law in terms of shrinking chips, transistors, I mean, was still alive and well. But what we're seeing right now is this kind of leveling off of our ability to shrink transistors as our primary means of improving performance. And so exascale, we just slipped under the wire here. 2022. So we knew that it was going to happen somewhere between 21 and 23. So we hit it right in the middle at 22. And so we have to ask, and then what? And that's where the, I wanted to point out how things really are starting to level off in terms of delivered supercomputing performance. So this is a diagram put together by Eric Strohmeyer, who's one of the stewards of the top 500 list of the fastest supercomputers in the world, which they've collected data for the past 30 years on this. And it's been an amazing exponential trend lines here. You look at the red line here, it's the #1 supercomputer on the list. The orange line is the 500th supercomputer in the list, and then the blue line is the sum, and just amazingly straight exponential trend lines that historically we deliver 1,000 times performance improvement in the supercomputers at every level every 11 years. And that's been, this is according to the, of course, the LINPACK benchmark, which is a very floating point heavy benchmark. But now if we look at today, the past 10 years of performance growth and zoom in, this trend line has really fallen over, where we're seeing in the past 10 years of growth, we've gone from traditionally 1,000x every 11 years down to 10x every 10 years. So the effects of the tapering off of Moore's law, at least as far as Moore's law being transistor shrinks, we're seeing this writ large in the delivered performance we're seeing from production supercomputers, and that's not good, because if we have a new Moore's law of scaling, we would still end up with IT, according to this most recent report from the semiconductor, can't remember the name, but basically, if we continue on our current growth line and we had a new Moore's law alone of scaling, then we'd still see IT growing to 30 to 40% of our primary energy, which is would be unsustainable. We'd never hit our climate goals if we do that. We need to create a new Moore's scaling where we can get the energy per operation down to femtojoules per operation in order to hold it down to 8%, which is what of primary power, which is what it is today. And this is because when we look at emerging applications like augmented reality, AI, machine learning, autonomous vehicles, there's still a 10 to the third, 3 orders of magnitude to 6 orders of magnitude gap between what we're currently able to deliver today in terms of energy efficiency and compute in a fixed power budget, and what's actually required of these apps. And they are really driving that enormous growth in primary IT power consumption in the future, particularly in the data center space. So, I always like to cite Neil Thompson. He's the only person I know who's both an economist, but also has an advanced degree in computer architecture. So he's at MIT CSAIL and MIT Sloan School. And consistent with the heterogeneous integration roadmap, they see that it's no longer going to be a market focus. This really comes from the HIR, but if you can see his papers, the economic impact of Moore's law, plenty of room at the top, what's going to drive performance past Moore's law, and the decline of computers as a general purpose technology. They speak in detail, both economic analysis, but also computer architecture analysis that shows that our old market was built on transistor scaling, which led to better performance and cost, which led to market growth and reinvestment. That's the old virtuous cycle, but the new virtuous cycle is really about delivering on system performance for your target applications. And in order to deliver system performance, you can no longer simply architect hardware decoupled from the algorithms and the software and the applications run on it. That, it's not just going to be hardware, software co-design. It's going to be hardware, software, and algorithms and all of these things need to be co-designed together. And this is the top of the stack rather than what has traditionally been driving things, which is the bottom of the stack, the shrinking of the transistor. And this is going to be the new reality that we're going to gear up for in the future to deliver improvements, the next 3 to 6 orders of magnitude of performance improvement. And specialization in the short term, this is going to be the approach that that industry is going to need to adopt in order to extract more performance from a resource limited environment. In fact, this is how, it's not just a computer architect's fantasy, this is how biological systems extract more performance from resource limited environments. So, in the old days of Moore's law, when there's plenty of food around, then you end up with these powerful general purpose raptors like this eagle here, which is really where we were at when we had the x86 Xeon or the IBM power processors. But once we have a resource limited environment where the food becomes scarce, or in our case, post-Dennard scarcity, you see the environment or the birds respond by having many more smaller animals. So in this case, we have, half a dozen really aggressive sparrows, which is really what the Intel Knights Landing, AMD, or the Caviar Marvell ARM-based systems, and really GPUs. A whole bunch of lightweight threads, but a whole lot of them. And this is how computer architects respond, but it's how nature responds too. Now, if you have even more food scarcity, then you end up having the critters going after different food sources. And they end up, Darwin's birds here, end up developing specialized beaks to go over those different go after those different food sources. And so this is where we're going to be going towards with post-Moore scarcity. And we're already seeing this happen in Apple, Google, and Amazon, where they're actually architecting their own chips that heterogeneously integrate many different kinds of acceleration together into the chip to target different parts of their workload, since they're the end consumer or user. So that's leads to this future direction for post-exascale computing. We went from general purpose CPUs to many core plus GPU acceleration, and the path into the future is really this, what we refer to as extreme heterogeneity. But the research question that we have to ask as we move in this direction is, what are the right specializations to include? What's a cost model that can make this sustainable? Because we know we can't afford to spin our own chips from scratch. We've been there, we've done that. That's what supercomputing was back in the days of Cray vector machines. And we learned to actually align ourselves better with industry after the attack of the killer micros. So how can we make this affordable and sustainable? And so, we see the chiplets and also the licensable IP ecosystem that goes together with that is the way to make this practical and affordable specialization, where the IP or the chiplet is the commodity and not the monolithic chip. So, we need to understand what's the right partnership and economic model for that could serve for the future of HPC. And that's why I spend my time. This is a slide I use to show my colleagues that, we did this pivot 20, 30 years ago to align ourselves with industry. We need to keep our eye on what industry is doing, and heterogeneous integration roadmap is a real detailed document about what is the industry doing about this. And we need to figure out how to plug in and leverage that, because this is the way we're going. So, one of the interesting other features is this convergence between the HPC and hyperscale data center strategy for agile specialization that pushes us towards this heterogeneous integration. So this is a great picture from DJ Dharmesh Jani from Facebook, describing, the data center view, the hyperscale data center view of the future of large scale computing. Just like us, they saw the area of the standard computation, the universal computation, and we split into this thing where now we saw CPUs and GPUs targeting specializations for AI and different parts of their workload. And what they see emerging is this need for, like I was describing, HPC needs to learn this, extreme heterogeneity, extreme specialization to target different subsets of their workload. And again, this is consistent with the heterogeneous integration roadmap, moving from a transistor focus to a system focus and having systems that are specialized for different parts of the workload. And so this is driving them towards a future of specialization. But the other observation is from Dan Reed. You can find his article on Archive, which points out that, Attack of the Killer Micros, we realigned ourselves with the microprocessor manufacturers, IBM, Intel, HPE, and we found out how to create this 80-20 rule where the 80%, the broader market is driving 80% of what we need to put into the supercomputer, most of which was focused around the processor and the server class boards. But we were still able to concentrate on the 20% to specialize the interconnects and other aspects of the system to make them supercomputers and serve the scientific workload. And that was the big realignment of Attack of the Killer Micros, was realigning to take advantage of this broader market force. But what Dan points out is that the market now is really, the electronics market is no longer dominated by the microprocessor folks, but really looking at the Microsoft, the Apple, the Google, and Facebook. These companies are really the new bottom for this Branscombe pyramid that and we need to figure out how to rebase our Branscombe pyramid so that we're aligned with what those hyperscale data centers are doing. And what those hyperscale data centers are doing are creating their own customized tailored systems, and they're building it on top of advanced packaging in the chiplets and specialization. So, there's an open chiplets marketplace is forming. This is one path forward is the open domain specific computing architecture, which is part of the Open Compute project, which was created by the hyperscale data centers. The other is UCI Express, which has a lot of our traditional players like NVIDIA, and Intel, and IBM on board. Regardless, this is open standards for die-to-die interconnect to ensure that we can mix and match chiplets to create different specialized system and package to target different workloads. Licensable IP, with by third parties lowers the cost barrier of specialization, but also leveraging this economic model with the chiplets that the hyperscalers are creating together with the microelectronics industry in order to make those, to lower the barrier for specialization. So by leveraging this new baseline and extending to support HPC, we have a smaller incremental cost for HPC to play. Because, right now we're looking at HPC might be getting too small to attack the city here. The amount of economic non-recurring engineering expenses is becoming unsustainable for the HPC people to differentiate themselves. So really, could be the new 80-20 rule, could be enabled by chiplets to build up a library of reusable accelerators, some of which target HPC, but interoperate with the chiplets that are being created for the broader ecosystem. And this interoperability is the future path for sustainability for our ecosystem. This is a old DARPA picture, but the notion here is that we get our access to commercial IP, but rather than being the IP being the monolithic chips, we can mix and match commercial IP for memory, SerDes, processors with reusable function blocks for specialized targeted algorithms like FFT, QR decomposition, and also some big data movement type capabilities. Again, by co-integrating within the package you minimize electrical data movement distance, and you can create a wide variety with the same set of Lego pieces, build a wide variety of custom solutions at a lower incremental cost. So Bill's already shown this picture. This is the last year, the ISCA meeting. AMD basically laid out what the economics were of going to chiplets. And the important thing is they get to do known good die testing for dies that are much smaller. And so there's more die survives the testing process. But also they can have, they're no longer reticle limited. They can actually build super chips that are larger than the reticle limit and do it at a fraction of the cost. Plus be able to support a multiple SKUs using the same set of chiplets arranged in a different fashion for different markets. And in fact, we've been having discussions with AMD about their chiplets and whether we could get into the package. The HPC people could get into the package and create a custom SKU for HPC because AMD does have its semi-custom unit. Well, this went from an internal discussion between the US government and AMD into being a core strategy for AMD, where they actually are opening up their internal chiplets architecture for third parties, such as the US government, to drop in their IP there and augment the IP that AMD offers. So this is a very exciting development and is aligned with what we see as the future for HPC. Overall, ODSA, as I described earlier, which is an organization created by the hyperscale data centers, is really pushing hard on creating open die-to-die interfaces, standards that enable multiple sources for chiplets to interoperate in the package through their bundle of wires interface, which supports tunneling of AXI, protocols like AXI and PCIe, and also the UCIe, which enables CXL to be the die-to-die interface. So they are pushing for this open chiplets marketplace which is facilitated by having that open die-to-die interface, reference designs that show end-to-end how you could assemble these chiplets together, and reference workflow flows that include everything from the high-level ASIC design and tools for ASIC design down to the foundry processes and product partners for integration of those chiplets. And so this is their vision for the future for hyperscale data centers. We in the HPC community want to realign ourselves to be inside of this chiplets marketplace, which is huge and already growing, much like the heterogeneous, a lot of these partners you'll see in the heterogeneous integration roadmap partnership diagram. But here's the big ticket item here is that, we're not going to create all of the necessary specializations on day one. The idea is that over time, HPC can build up reusable building blocks, reusable specializations over time that can serve our workloads. Because you can see here in the cell phone market, they have 52 different discrete accelerator blocks that go into the Apple A series chips in order to give them a leg up over general purpose CPUs and GPUs. And in the way that this is affordable, even for a large entity like Apple, is by building up a library of reusable function blocks, reusable chiplets that can be reused by multiple applications. And that's how we make this affordable and sustainable, is building up that repertoire, building up that library, and increasing the amount of reuse so that you don't have to start respin a chip from scratch again each time. And that's how we're going to make this sustainable and affordable in the long term. So I'm going to stop there because I know that we are short on time. We're 6 minutes after the hour. My only other part of this is really that co-packaged optics and chiplets for co-packaged optics will enable us to get over this power wall for off-chip I/O, which is really hurting us now. This is a diagram from DARPA, Gordon Keeler. Really, the source data is from NVIDIA, which shows that the total power in the package now is starting to cross over the total power required for off-chip I/O. And that's also not a sustainable path. So the only way to get around this is, of course, co-packaged optics. And there's this amazing convergence of technologies. Of course, there's the advanced packaging, the chiplets technology, where you go from high SerDes, which is just burning a hole in these chips, into wide and slow, copper pillars or solder micro bumps that can operate at, a slower data rate instead of hundreds of gigabits per second, 10 gigabits per second, which is much, much more energy efficient. And same with silicon photonics, where you can operate ring resonators at 10 to 25 gigabits per second, but have many of them co-integrated together on a photonics chiplet to encode light on separate frequencies, so you can achieve terabit per second per fiber performance. And then once you get it in the photonic domain, you can go anywhere in the system. And the last and the most recent development is the emergence of comb laser sources. Rather than having a discrete laser for each frequency of light, being able to have a single laser generate a comb with hundreds of different frequencies of light. The convergence of these technologies is really going to revolutionize and launch co-packaged optics. There are commercial companies such as Ayer Labs and Escape, which are marketing solutions, real solutions that can be deployed at scale and co-integrated in multiple vendors' SIP designs. So I'm going to skip ahead, and we're going to end there. So, we have to think seriously about how to put specialization productively to use for science. This is going to be co-design now that dips into applied math and algorithms in addition to the software and the hardware. You have to reevaluate the business and economic context, the economic model that we use for the design and acquisition of HPC. And we want to model solutions for the global climate crisis without contributing to global warming. So we want carbon neutral HPC by 2030. And that's our big, that's our new thing. That's what we do beyond exascale. It's not zettascale, it's carbon neutral HPC by 2030. That's it. So any questions? Can't quite hear. Is there a microphone you can use?
Yeah, we've got.
Oh, there you go.
Thank you, John. I have one question. Since you skipped your last slide, I'd like to focus on that one.
Okay.
Optical, just a photonic interface, so the bandwidth I/O. So do you have any example or the work you are doing in terms of optical interconnect, the further penetrating into this packaging?
Yeah, so we work, so I'm more the computer architect in this. So we have a project as part of the ARPA-E Enlightened, which is photonic co-packaging for energy efficiency, and it's led by Karen Bergman from Columbia University. And so we're using her optical system and package in order to experiment with system resource disaggregation. And so, on the architect, and we're also involved in this is John Bauer from UC Santa Barbara with the comb laser sources. You've got NVIDIA, Larry Dennison is involved, and we have Cisco and Microsoft Research involved. Microsoft for the mega hyperscale data center part. But what we're looking at is once you get into the photonic domain and you're able to connect from GPUs to disaggregated memory at high in-package speeds, which is the experiment, then we can reconfigure nodes to target different workloads. Because what we find now is that the current approach to designing a supercomputer is you put all the things you need into each node, even if you don't need them for a particular subpart of your workload, and then you replicate and repeat and scale that up to make your data center. And so the utilization of accelerators and memory is like very inefficient. It's something in the order of 20% of the resources are utilized effectively at any given time. Resource disaggregation using this photonics co-packaged optics enables them to only patch in the resources that they need on a job-by-job basis, whether it's training, inference, data mining, or graph analytics, and we can push our utilization up to 90 to 95%. And so that's a lot more energy efficient, and is also a way that we can specialize on the fly for different jobs. So that's Karen Berkman's PINE project, Photonics and Hyperscale Data Centers project.
All right, any other questions?
Yeah.
All right, thank you, John.
Sure.
Thank you, Vincent. Thank you. Mask have come up, as you can see, from the same person. So this will be a very quick, lightning talk on HPC and data centers chapter for the heterogeneous roadmap from APS. So I co-chaired this week with Dr. Del Baker of IBM, and you will find the documents for all the chapters and contact information for the chairs on the EPS website. We welcome volunteers to serve on this weeks. You always need fresh blood to bring in new ideas, replace some of the ones who have moved on. Okay, so the intent of our chapter is to really press home the fact that heterogeneous integration requires a completely different way of designing your platforms. You have to think holistically at the system level. So that means, not just algorithm, software, and hardware, but even the computing paradigms, the processing paradigms. You have to think of really unconventional things to make things scale at the way we are used to. So specifically for HPC and data centers, the products that are heterogeneously integrated have to address the diversity of the chiplets and the solutions that are there. Some of these are pretty traditional, many of them are not, especially the ones that are more promising. You have to deal with interconnections at different scales between chiplets, with the interposer outside the package. You have to worry about power conversion and delivery, security issues, so on and so forth. And one of the interesting differences that our chapter has with the other chapters, where you can quantify some trends and make some predictions over 5, 10, 15 years, it's not possible to do that with the HPC and data center products because they are evolving. Architectures are changing. That said, we do make some projections that are at the end of the chapter. So it's very clear why you need heterogeneous integration in the HPC and data center market. When you operate at advanced nodes, the design costs are going to kill you. And you can see that in the bottom chart there on the right. More importantly, you cannot maintain the size of the chip, which is an inherent assumption behind Moore's law, that you keep the die area the same and pack in twice as many dies. The cost per unit area at advanced node is again going up more than exponential. So your hands are tied. The only thing you can do is to use smaller pieces and integrate them tightly to realize the system that you want. And the challenge today is it's not the power that you dissipate in the transistors. It's the energy you spend in moving data from point A to point B, from one part of the chiplet to another, from one chiplet to another, chiplet to the interposer, the system to the outside world, and beyond that in the networks and whatnot. So that's really the showstopper. Okay, so in the HPC data center segment, I have listed some of the drivers. Cost per unit array is going up. Application-specific accelerators are turning out to be significantly more energy efficient than general purpose things. And I'll give you some examples, okay? Nodes are not scaling. Circuit features are not scaling commensurately with the node. And you can read many of the articles that are there, 3 nanometer is not delivering what it was expected to deliver because things are not scaling. Okay? Areas are not scaling as commensurately. But the biggest drivers of all are the applications. It's not just HPC, but analytics on demand on the web. Okay, big data processing. You have to collect, move, process enormous amounts of data. You have to do processing at the edge to overcome that bandwidth bottleneck. So when you collect a lot of data, you probably have to process it very close to the point of collection. And then blockchain processing, which is not just for Bitcoins, but for doing other useful things. On the bottom right, you see one of the primary reasons why you need to really think differently, the system scale. And that has to do with energy efficiency and the energy supply. There are a couple of papers that have basically looked at the trends of traditional platforms, how they evolve, how their energy efficiencies are improving. And we are looking at the deployment, and in about 10 to 15 years, the world would not produce enough energy to even power the systems that we are developing now. So we really need to think of a different way of designing systems, the chiplets and the components, to pull this off and not run out of the energy sources that we have. So heterogeneous integration is the panacea, of course. You can integrate diverse types of chiplets, non-traditional chiplets along with conventional computing, whatnot. And the goal is, to produce a whole, namely the system, that is greater than the sum of the parts. The system does better than what individual chiplets can do added up together. So in the HPC data center segment, needs are very specific, very geared towards application. You have to integrate diverse components, and disaggregation is the name of the game. Take the function that you want to realize, break it down into simpler functions, and realize each function as efficiently as possible, and then hook up the chiplets together with a low latency, high energy efficiency interconnect. So here's an example. Machine learning and AI applications have permeated everywhere. You have some components running on your cell phone. You have some things tied to your camera, on the drone, on the vehicles, automotive sensors, and it's all over the place. And there are other applications of AI that go well beyond that. The practice that we are used to at this point is that, take general purpose GPUs and use them to implement your neural networks. That's not sustainable. So other solutions have cropped up. And one of the most interesting solutions has to do with, a couple of things. A, you do not need the full-blown power of floating point arithmetic to address all AI machine learning problems. That is like taking a bulldozer to kill a fly, not even a hammer. It's terrible, it's energy inefficient and whatnot. Okay? Instead, you can do it at lower precision in your calculations. And many approximate computing machine learning accelerators use this principle. Going beyond that, we could take advantage of analog computing techniques and realize energy efficiencies that go, beyond the ceilings that you have with traditional platforms. And there's a chart from IBM that's shown on the left, okay, where they have a roadmap to improve the energy efficiencies. Okay. On the right, there is a processor from IBM that was developed. It uses phase change memory devices to do the analog computing inside the memory itself. So two things have been used here, okay? Analog computing and processing inside the memory so that you consume the data right where you have it. And then there's this product from a company called Mythic. Many of you have heard about it. That's a single chip that realizes 25 tera operations at 1/10 the power that you'll use to spend on a room full of GPUs. So these developments are happening, and these are candidate chiplets that can be used, examples, to do what you need. Okay. Analog memory technology features heavily into this story. Okay. They are significantly more energy efficient. You can store 7 bits of information in a single cell in some of the analog memory products and store the weights, and these analog memory devices would last for 10 years. They'll not lose capacity. So that's the kind of things that I'm talking about. Really non-traditional kind of things. Okay, very similar story for non-volatile storage. RAM as you know it or DRAM as you know it may not be scalable. So there are new memory technologies that have RAM-like capabilities. They have RAM-like lifetimes, and you can write them to death. It's not like a flash where 20,000, 25,000 sustained writes would kill your device, but something well beyond that, pretty much like RAMs. And by the way, conventional RAMs do have a finite write lifetime. It's not infinite as many of us think. So this is how many of the interesting actions would take place, the write endurance and capacity trade-offs. Interconnections are the key to this. No matter what people think, photonics inside a chiplet, inside a package is still not practical. Yes, you can generate papers, you can do interesting DOE projects like the one that John mentioned at the end. But to put it to production, to deploy it widely is a very different ballgame. However, optics has its benefits, and you will see that at the package IO scale, there are realistic solutions that are emerging, production quality, shovel ready for deployment. So anyway, interconnections are needed in a system in a package, aka heterogeneously integrated system, to give you tight coupling. And what you mean by that is you have a high bandwidth connection, not just high bandwidth, but also low latency. In the world of HPC and data centers, it's not just the bandwidth, it's also the latency that matters, how quickly you can talk. Okay. So these are the challenges. Okay. In addition to the performance metrics that we need, bandwidth and latency, there's also this challenge of energy consumption. You want to transport data as quickly as possible from point A to point B, and you need low error rate and reduce footprints. So all of these have driven some of the solutions. The industry solution has been to use conventional copper interconnects because they can be produced in mass scale. Okay. We have face-to-face microbump speech in products that are in the 10 micron scale, coming down to 5 microns. You're soon going to have vias that are at the nano, hundreds of tens of nanometer scales, and so on and so forth. So all these things are happening as we speak. And standards are evolving. Standards for the interconnects, the interface, the physical design, macros, and whatnot. And you can look at chapters 22 and 23 in our roadmap, but these are covered in some enormous depth. So here are some examples of photonics advances. John spoke about the one on the top, silicon nitride microresonators with a very small footprint. And then also, the basis, that's the basis for designing a dense optical power supply that would emit wavelengths that are stable at different wavelengths. So instead of cooling 20 or 30 transceivers in your package or on your PCB, you have to aggressively cool it in a stable manner, only a small part of your system. That is great because the bad news is that all these photonics transceivers, they operate in a very comfortable temperature range. Temperature cannot vary by more than 4 to 5 degrees Celsius at worst. So instead of cooling the room or the entire board, you have to cool only a tiny part. So this is probably the way to go. And Intel also demonstrated products with co-packaged photonics that gives you significant energy efficiency, and you can convert the photonic signals to electronics and switch it electronically with low latency. There are products that are coming out. Power conversion, distribution, and power management is a issue in general. Two things are happening, okay? Given the advantages of heterogeneous integration, there is always a tendency to pack too many functions inside a package. We can't stop that. That's an expectation that you're all used to. But at the same time, what is happening is that the supply voltages are coming down. As the power footprint is going, the supply voltage is coming down. And what does that do to your current? The current that you have to supply to the package would be hundreds of amperes, even thousands of amperes in the unforeseeable future. And when you have so much current flowing through tiny conductors, the ohmic drops, the I squared R drops come into play. So the solutions are the obvious, okay? Do not supply high voltage to the package. Supply power at a higher voltage than you're used to. 48 volt, 12 volts, 24 volts, people have spoken about this. And then convert this locally at the point of load inside the package. This requires low area footprint converters that can convert it with very high efficiency across a wide load range. It requires the development of new materials, inductances in particular. Noise mitigation is a challenge when you integrate analog and digital. You have to worry about the quality of the power, the harmonics, noise, and whatnot. So there are solutions I have listed. You can read this. I'm not going to bore you with the details, but there are emergent solutions. And Doug would talk more about this during his presentations. That's chapter 10. Thermal management is an issue. Academics, in particular, tend to design exotic cooling solutions that nobody can implement. Microchannels. There was a company that was started by a faculty that didn't last because it's obvious. You can't do those exotic things inside a package and produce it in quantity. Yes, 1, 2, 10 of that works. Okay. So, to me, as an architect and as a systems person, the only way to control power is to really two things: system level design it from big to begin with, and come up with better energy efficient devices. So, we have some devices that are in the horizon, like, spin transistors that go beyond the gate around transistors, chip transistors and whatnot. And you will see some of these things. But the big challenge, so far as heterogeneous integration is concerned, is cooling 3D stacks. When you have chiplets stacked in 3D, that is a much bigger cooling challenge than anything else. So directed cooling, immersion cooling, liquid cooling are solutions that are practical, that are being used, and that can scale up to a limit, of course. Okay? And again, you can look at the solutions in the roadmap in chapter 20. Security is an issue for many reasons. You are designing a system, not just a single chip. And there are unique security challenges for heterogeneous integration. When you bring multiple chiplets from different vendors close to each other, there are unintended coupling, unintended security threats that you did not have to think of when you had a single chiplet inside a package. You could have electromagnetic coupling, thermal coupling, whole variety of attacks. And you have to look at the supply chain, look at system level solutions, and these are all discussed in chapter 19. Quantum computing is another thing. You can have quantum computing systems that use room size dilution refrigerators to cool the qubits to the millikelvin temperatures that's needed. Or you can cool a small piece, and there are qubit designs that are evolving where you have to cool only a tiny part of the system as opposed to cooling a room full of liquid. Heterogeneous integration plays a very important role here in integrating qubits, the measurement circuit, the manipulation circuits, and whatnot in a single package in a small form factor. Yeah, you can look at chapter 2, or chapter, but section 5. So I will stop here. I don't think there are time for questions at this point, but I do see a slot at the end for Q&A, right? Is that how you want to do it? Okay. Yeah, if you have a burning question, I'll try to answer it. All right, so we'll wait till the end. Thank you. Okay, Internet Explorer should work. Okay, it's not set up, unfortunately. Benson, I can't play you. You gotta come in. What did you use? Explorer? Oh, you have a PowerPoint. Okay, that makes it easy. Sorry, thought it was a PDF. Okay, all set then.
How's that? A little louder? Okay. Okay. So good afternoon. I'm Dan Blass from Lockheed. And I will point out Tim Lee of Boeing, who's the co-chair. He's the one who does most of the heavy lifting, and this is really based on his slide deck. So if I stumble once or twice, I'll apologize for that. I start out with kind of the importance of the domestic supply chain for our industry. I feel like a lot of this slide deck is going to be fairly redundant after the last couple of days, and a lot of discussions that have been had over the CHIPS Act and the NIST things that are going on and all that kind of stuff. But the main thing is that you know, the packaging, assembly, and test is Asia focused, and that's a problem for us. You know, semiconductors are critical for our security, and the flow of that overseas is a problem. And then the other thing here was this comment on incentives are needed for us to compete. So yeah, with the CHIPS Act, we certainly have lots of incentives that are going to be rolled out. I'll just make a little plug for what I would think helps me the most, which is when it comes to getting the advanced semiconductors, it's easier for me to get those semiconductors than it is to get the substrate I need to put that on. So I would vote for investment in the packaging and test arena to help us. So some of the unique things about, am I doing okay? So talk about some of the unique things for defense microelectronics. The picture on the screen is kind of like an operational picture view that's a few years old. It talks about the things that we want to achieve for the warfighter, and a lot of it has to do with we have all these platforms that we want to have interconnected. We want them to have protected links, lots of links, and decentralized systems. And so when I look at some of these things, sort of the way I look at it is, am I trying to make a flying data center is one way to think of some of it. Some of it is because so much of our things are about sensors. So building that sensor, is it a flying base station? Is it a flying data center connected to a base station? How do we generate high quality sensor data, the sensors that we want to go out and understand the world and interact with the world? And how do we use that data that's coming in and make sure we're taking full advantage of that, taking advantage of it fast enough, being able to communicate back, but then also being able to be decentralized enough that we can act on data close to the sensor in a sort of an edge processing feature, and then also be able to act at data at that level. Okay, so this slide here is a few years old, talks about some of the unique things that we deal with when it comes to defense electronics. It's going to be things like the fact that we have extremely long product cycles. So even by the time we get done going through the design and development, some of the components in the system that we're designing in the system may be starting to go end of life and obsolescence versus the commercial products, which have a very short lifetime. Typically, we're looking for very high performance. So we're looking for access to the advanced nodes and the advanced packaging to put the systems together. And then looking at high reliability, harsh environments, in some cases, very extreme environments, which is not something that we really have included in the roadmap. things like high temperature electronics and stuff like that. The roadmap's more focused on how we interact with more or less the traditional supply chain that's being developed. Things like I mentioned the long product life cycle where we've got things working. It's going to be in the field for a long time. We've got to interact and talk with systems that have been in the field for a long time. And then the other thing that tends to affect us is the relatively low volume that we have. Whenever I talk with potential suppliers who are not necessarily familiar with working with us in the defense industry, talking about when we say high volume, what does that really mean? It's generally different from what they're thinking or what they deal with in the commercial. But in terms of what I think we need to do in terms of defense electronics, the commercial model of that type of high integration of how we shrink things is really useful for us. You know, our products tend to have been, we make an electronic box. Inside that box, you have a power supply card, you have some processor cards, you have some RF cards. And really what we need to do is to figure out how we, with advanced packaging, bring that in, shrink that down to try to get that down into a single system instead of discrete units. In terms of our roadmap and the influences on it, a lot of it comes from DARPA, the DARPA programs that have been around. I'm not going to go through these in too many detail. I'll point out the new NGMM that just came out that BAA very recently, which gives us an opportunity here in the U.S. to move beyond sort of the state-of-the-art, the SHIP programs that we now have access to, and how do we go to 3D heterogeneous integration. And when I talk about how I'm going to bring my systems and shrink that down, I really want to see how I can bring in these other things that go into RF systems, the wide band gap semiconductors and things like that I want to bring in and co-package with the processing to shrink that system down. And 3D heterogeneous integration is a great way for us to try to do that. Right now, as I go forward, I'll talk about the CHIPS program obviously is a seminal one, and getting everybody in thinking about how we're going to create these systems. In terms of the chiplet library, that's something that we still need. We don't quite have the library that we want. Within the roadmap, our chapter roadmap, we talk a lot about AIB. We'll have to update that as new standards come about, but how we can interface those chiplets together is an important thing. It's just a practical thing for me. I don't really care. I just need the two chiplets to be able, one, I can go buy them, and two, I can get them to talk together without having to do a new spin. Some of the other programs, I'll focus mostly on the SHIP program, which is are up and running for heterogeneous integration. There's the Intel program, which is very useful for us. And then, so this is the digital portion of the SHIP program. And then Corvo has the RF SHIP program. When these came out, I was a little bit disappointed to see that we had two different ones, a digital one and an RF one, because I really want those things to be co-packaged so I can shrink things down. But I understand that at the time, this is really state of the art. State of the art is having them separate, but being able to do it at high density. And then the 3D HI program, I think, is the way that we can better try to bring those together and co-package them. Running out of time here. The NIST programs we talked about, the CHIP Act, lots of information about that. So I'm not going to go through the slides on that. But there are a lot of DoD efforts on how do we strengthen the capacity that we have within the U.S. to create these new systems and build those. So lots of great things going on. And then, so next steps for the CHIPS Act, what's that funding? How is that going to get rolled out? How are we going to use that to to our best advantage and not waste some of that funding. It's a whole lot of funding to get spent over 5 years. Continue to monitor the NIST activities and their road mapping. In terms of the A&D roadmap, we want to expand coverage to better cover activities from other parts of the world. We're it's been fairly US and DARPA centric in how we have it laid out. So we're looking at getting some other inputs into the roadmap. And I think I'll stop there. So any quick questions, or we can hold them for the panel session?
Hi, good afternoon. My name is Shafi Saiyed. I co-chair the MEMS and sensor integration technical working group as a part of this roadmap effort. I'm a co-chair. Marianne Meher, who's the CEO of Soft MEMS, she's my partner in crime, trying to put up this chapter. So what I'm going to do is, these are team members, just a disclaimer. The stuff that I'm presenting today represents the work of this group of people and some other members of the technical working group who we have a brainstorming sessions and give us some inputs. In the last line, I put it in red. If you look at the list and some of the technical working group people that we have, most of them are from the industry. As a matter of fact, we don't have a single person in our technical working group who's from academics. So Bill and I have been trying to get some academics help us and volunteer and get some theoretical perspective, some different views. You know, we are from the industry. When we come from, we are very biased in terms of cost and can you scale it as a production devices. We want to remove that bias and get some academic viewpoint. So if not from the academic perspective, if you are here, if you would like to volunteer, if you want to just have a brainstorming session with us, please help us volunteer. Okay, so throughout this symposium yesterday, early in the today, what we have seen is high density scaling up, data centers type of requirements, right? What we come from, and we like to say in our sensor group, we typically say, let's get back to the real world. Because sensor is right at the forefront. You have all these data sets. I'll show you in a very simple way in a signal chain, how the signal chain gets processed. But before we go there, where the sensors stay? Sensors is right the front for interacting with our world. Nature is not binary, 0 or 1. It's all analog. Whether you take motion, sound, optical, lights, magnetics, anything you talk about, these are all natural phenomena. The sensors actually have to talk to them. That's the big difference with the traditional microelectronics. So if you think about it, each of these different physical phenomena that we have, if you want to develop sensor packaging at a component level, I'm not even talking about system yet. Even at just at a component level, you have some unique requirements because they talk to real world. They have to stay right at the edge. If you want to design a motion sensor for a crash airbag, it has to stay inside the car at the right location. You can't just put it in a controlled environment somewhere in the data center. Same way with acoustics, MEMS microphone. It has to stay and talk to the actual environment. You have to design it differently. So if you think about this, MEMS and sensor integration, it's a very broad topic. As a small group, it was impossible to capture everything. So what we decided was we'll start from first inertial MEMS sensors. And that's because most of the team members that we had, they were from the inertial MEMS sensing group. So we started at that, and that's limited our scope. So I mentioned about a signal chain. If you think about signal chain, you have sensors right in the world. You try to understand, you try to digitize that signal. You transform that signal. You take the analog world and convert it into binary, which is very, very noisy. Analog to digital converters, right? Amplifications, precision signal processing. You process that data, then you transmit it to the cloud. All we have done so far in the last 2 days, we've talked a lot about this. We have touched upon sensor a little bit, but most of the discussions is right at here. But to feed data to clouds and do the intelligent processing, these things need to happen. Okay. So what we are doing is we're trying to figure out, when we talk about sensors, we are not trying to create a roadmap or a challenge, understand the challenges or give some guidance. at a component level. We're not talking about inertial MEMS as a unit, not sensing unit. What we are saying is, how do we take that sensing unit and integrate upwards? Combine with data converters, amplifiers, combine with microprocessors. Remember, I'm talking about microprocessors. I'm not talking processors. Big difference. And then once you have that, take that data, take that sensing data and transmit it to the cloud so that it can be intelligently processed with AI and ML languages. So when you think about this, I'll give you an example. MEMS sensors, I mean, I don't know how many have seen MEMS sensors. They're very tiny, 2 by 2, 3 by 3, 5 by 5 millimeters. That's small. You try to add sense and convert. You try to add microprocessor. You try to add RF. When I was walking, I saw this example. It becomes this size. The MEMS sensor is smaller than the cap, but you add the processor, you add the data converters, you add the RF, you add the power to process the signal, it becomes this big. You're not going to put this big sensor on the edge. Okay. And second, if you sense that signal with the smaller than a cap silicon, how are you going to transmit it? There's not enough bandwidth to transmit that signal. So if you cannot transmit the signal, how are you going to apply AI and ML to interpret that signal? So what I'm going to do down the slides, I have a couple of slides giving example in automotive world, and I'll take an example of a medical wearable type of applications to show what I really mean, what type of applications create. So we're talking about how do we take this and integrate upwards along with the ASICs, passives, antenna, power sources in the same tiny little integrated package. And this is where the heterogeneous integration comes into place. Because if you think about it, sensors have their own microfabrication technology. MEMS is not an integrated circuit. It's a microfabrication technology. ASICs, this is the typical digital processing technology. Passives are different. Antennas are RF. Power source is completely different. These are multiple different process technologies that can be integrated in a small package, a real example of heterogeneous integration. So the challenge is the same thing. How do you take these signals, pass it up the chain, making sure that the performance and signal integrity is not affected? That's the question we're trying to answer. So when in our working group and some of the brainstorming sessions we have had, what we are seeing is it's application driven. If you think about, before we go there, all the components that we design in the sensing world, there is no Moore's law. It doesn't exist. Because these are driven by physics. These are driven by physical principles. You have a chemistry. If you want to sense a body's biological chemistry, if you want to sense chemical processes inside industrial factories, there's no lithography. They have a different physics. That's what is used to do the sensor packaging. So if you think about inertial MEMS and take example of inertial MEMS in different types of applications, what we are seeing is in the handheld and the healthcare type of applications where it's more about miniaturization, precision, WLCSP type of packages are quite used. So if you see this example, what you see here is you have this, that's a MEMS sensor, and that's the signal processing chip down there. Same here, you see two sensors here, and underneath that, there's a two ASICs, like a signal processing chips. They don't have microprocessor. They don't have RF here. They are hardwired on a PCB to take that signal out. And those are large PCBs. Here's an example of a consumer MEMS from M-Cube, which is just a sensor. It doesn't even have an ASIC. They're tiny. So what we as a group see that on these type of applications, it is going to have a path where the WLCSP is the one where we see a potential path for integration. Autonomous driving, industrial, aerospace, where they are characterized by long life, high precision, high reliability, need to have high stability over a long time, not just for 2 years or 3 years. What we are seeing is that's where the real challenges are in terms of how do you integrate. The example I gave you using the bottle is actually an industrial application. The sensor is tiny, but you integrate all this processing and RF chips, it just becomes huge. Okay. Just to give you a relative idea, this size is 26 by 20 millimeters. This size is 50 by 50 millimeters. That big. So it's going to be, the path for heterogeneous integration for sensors is going to be multiple. It's not going to be one single path. Here's an example of It can be just one single inertial MEMS, but how application impacts the specification, how you design them. I mean, if you look at the performance matrices, the names, the definitions of these, they're all the same. It's the same in-run bias stability you would use for designing a MEMS, for a consumer MEMS, for a navigation, or for anything. But the difference is in the actual numerical values. If you look at degree per hour, this is more than 15, and in navigation, it's less than 0.1. Order of magnitude difference. So the sensing that you design for this will be quite different than this. So the packaging that you will do for this will be quite different. This is just an example. Same thing if you look at power. On consumer and wearables, or even in the medical vital sign monitoring, this whole system must really operate on a coin cell battery. You're not going to have a monitoring system on a watch, on a wrist with a AAA battery, 2 AAA batteries. It's going to be just huge. So you really need to design that whole architecture. I think Kanad mentioned in his talk, the architecture needs to be addressed, not just stitching the components together. You got to have an architecture of processing, microprocessing, RF transmission in a way that consumes less power. Only then you can have a battery operated solution. Okay. I mentioned about application example. Here I will try to highlight the importance of transmitting the data bandwidth. If you look at a modern, you've heard about autonomous cars. Autonomous is just a generic term, but it can be used for passenger cars. It could be used for transportation vehicles, drones, agriculture equipments, anything you talk about. If nobody's driving the car, nobody's driving the truck, how you monitor the health of it? Who's going to track whether it's wear and tear is happening or not? Right? That's called condition monitoring. Here's an example of vibration sensing. Vibration is motion. Vibration sensing, where the sensors are inside the tire next to the pressure sensors. What they do is they measure shocks so that they can correlate that shock profile to tire wear and tear. They are measuring road vibration. So that data of vibration can be used for noise canceling inside the cabin. If you do drive an EV car, what's the big difference between EV and IC in terms of user? The noise inside the EV cabin is dominated by road noise. There is no IC engine. So there's the reports. So some of the OEMs, they have done some research, and the driver fatigue is one of the big problems in EVs because it's a road noise driven, which we are not used to. So what OEMs are doing is using vibration sensing to cancel the road noise. Imagine vibration sensors mounted, vibration and shock sensors mounted on 4 wheels, the data getting transmitted inside the cabin. Amount of bandwidth it will need. It's millions, trillions of data bytes. Because it's sensing data at every microsecond. So if you put an intelligent processor right there and transmit only the required signal, not everything, only the required signal, that's what will enable, that's what will help us understand the condition of autonomous driving. Because there's nobody there to check it. Nobody there to feel, oh, I had a shock, I had a bump. Here's another example. We talk about vision system for autonomous driving. This is an example of how a vision system sees the road or the objects around it. And here's the vision system output after sensing, most vibration sensing, using vibration profiles and canceling out those noise. And this is the clarity you get. Ideally, the industry is working to have even a better clarity. But with vibration and with vibration sensing, this is how the processing needs to happen. You're not going to transmit the signal to the cloud for edge, for data centers to process and then send it back to the car for that clarity because it's everything happening in real time. So you need processing right at the edge. But if you have to put a big batteries like I was mentioning, it's not going to work. So sensing is enabling. I'm just sharing some examples, and you can see here there are multiple locations in the car. There are these sensings occurring. You are not going to be transmitting these signals to the data centers. You have to process it right inside the car at a power that is very, very low. Here's an example of medical vital sign monitoring. This example, what you see is typically when you design a sensor for vital sign monitoring, for sensing purposes, these are the different metrics that you may use. Pretty detailed chart, but what I want to highlight here is the power consumption. This is a vital sign monitoring wearables. And these are right now consumer grade wearables. This chart is driven by the consumer based variables. It is not driven by clinical data set. The sensing data that comes out of these devices, they are used for sports purposes or some of our consumer applications. Doctors in the medical community does not use that data. Get to the medical grade level, the level of precision required is even more than. But the example here is, if you look at the power consumption, if you're just measuring steps, it's 1.8 microamps. If you want to measure fall, which is more important than steps in terms of medical health, you want to detect your fall, it's almost 2x the power. You want to combine all of this in a single sensor, single chip, imagine the amount of power you need. Just trying to highlight the importance of changing the architecture for signal processing and transmission. I'm just going to show some pictures on this. If you have the medical, which becomes implantable for the healthcare, what you have to add is form factor, biocompatibility, and hermeticity. Here's an example from Letty. They fabricated a very simple MEMS accelerometer. You can see the tip of the pen, that small size, which can be implemented in the catheter tube so that you can monitor the direction and the way you, at the speed at which you insert the catheter in the human body. That tiny a sensor. So when you talk about implantable MEMS sensors, you add all these factors. This is my, I think, last slide. What this chart basically did is just summarizes these different application areas here. This is the current state of art. These are the type of applications. This is the packaging we would use. Emerging applications, and what are the direction we as a group think the packaging will need. For example, in the medical and the consumer, you can see wafer level CSPs, thin sensors, EMI shielding, flexible substrates, biocompatibility. Thin sensors, thin profiles. I think if you go into the traditional microelectronics, you can grind down a sensor almost down to 50 microns, 75 microns, Z height thickness. I haven't seen this sensing group that we have, people, we haven't. You know what the minimum thickness of the MEMS sensor is? 500 microns, 0.5, 0.1, 0.5 millimeters. In a traditional microelectronics, we can do 50 micron, 75 micron thin silicon. That is a real bottleneck for WLCSP, pretty thick. And then on the high end side, where you have this automotive, aerospace, and industrial, we really to see that SIP-based modules, where you have to integrate RF communication in order to reach the edge and clean out the noise and only transmit the clean signal. Okay, I'm going to summarize it now. What we have done is we have already published the 2021 version. It's up on the website, IEEE website. You can take a look at it. What we are trying to do in 2022 is we're trying to link it with other cross groups. We are adding other foundational technologies. Ultra low power. How to do the packaging for that? We're trying to add that in clean processing. Packaging materials that will enable MEMS to work along the signal chain. As I said, we want to put these MEMS sensors next to traditional ICs, but the packaging materials that you use for MEMS are unique, different than traditional ICs. How can we combine them? That's a big question for the materials processing group. And then, some of the emerging, integrating the emerging MEMS sensor like functional blocks, EMI shielding, tunable filters. Because if you want to transmit the signal, you got to work. You have to have solutions around this. I mean, if you think about, if you ask any sensor guy, he'll say, "Are you putting RF chip next to MEMS because of the interference?" MEMS sensors, they work in microfarad, picofarad capacitance. That down, that small. Okay. If you put an RF chip next to it and use it for transmission, it will interfere with the functionality of the MEMS sensors. So how do you do the shielding in that small spaces? That's a question. And some of the other sensors that we are trying to add. We only talked about inertial sensors. We are trying to figure out, can we add more chemical sensors? So we're looking for volunteers. If somebody in the chemical sensing world can join the working group. Okay, that's my last slide.
So this chapter looks at medical, health, and wearable. However, I must admit the focus has been quite heavy on wearable because many of us in the community are involved in this. And I'll put out a call for the end, and we received a bit of input that we are looking for those working in the actual hard space of medical devices, including imaging systems and other, to also chime in, because the fullest breadth of heterogeneous integration for healthcare includes all of these other things: imaging systems, human health monitoring, as we'll talk about, and implantable devices, which these days become more and more diverse, various in and non-body diagnostic systems, and of course, many other things. And as we noted, in particular, the pandemic, at least in the wearable space, has attracted a significant interest and drive to perhaps take some of these things a bit further than some of the prototypes that we're all playing with these days. That being said, in chapter 4, as is, we have focused on human health monitoring and diagnostic systems, taken advantage of our team's diversity and a variety of skills and perspectives. Important to note that wearables once upon a time were, still somewhat are, things that you buy for your personal use. Really what is needed and what is happening now are these medical wearable devices are now becoming quantified medical grade systems, such as the type that Andrew from GE spoke on this morning, and that I'll show you briefly and remind you what it looks like. So these systems have to be truly like the bedside, the benchtop type of medical equipment that is reliable, performs, is accurate, is calibrated, all those kind of things, because nobody ever wants to be responsible for a misdiagnosis because of some sensor on a person's body. In addition, we also see fluid and biomarker analysis as being something very important. We initially looked at wicking of sweat, absorbing for ions and measuring ion concentration, but also looking at either blood, invasive, or slightly non-invasive interstitial fluid as a way to diagnose disease, and perhaps diagnose disease before you actually feel like this. Thanks to Bill, he's so helpful in many things to all of us. He asked me, gave me an assignment, as he's been doing since I knew him when I was a new hire at IEEE. And he said, at the next ECTC, which we had this earlier this year, you will have a panel on medical health and wearable. Anyways, it worked because, as you know, conferences, we were very lucky that this conference worked well in person. Most everybody is here, but as Bill remembers at ECTC, it was still kind of hybrid in places, particularly. So we had a number of individuals, and Christine is here from is here. And, Richard was attending, but we have a representative who's going to talk to us about the work there. Gave us some different perspectives. So trying to get into Medtronic and trying to get them to contribute to the roadmap may be possible. Scott did participate in this, and he gave us a very graphic display of the history of such important medical devices as pacemakers, defibrillators, and cardiac monitors. How they've evolved from size, from the 2G type of unit shown below to something that is so small that it fits in the muscle of the heart, actually implants itself and performs its work in place within. And of course, looking at the image to the right, you can see that half of it's battery and the rest of it's electronics. From what we gleaned, traditional types of electronics, standard kind of packaging, which of course would be the most reliable for such a device implanted. We heard from Letty about their use of chip and flex and wafer level integration. And of course, we just heard that from Shafi about encapsulation and hermetic sealed box. But the idea here is do all this on a wafer, make it very small, thin the wafer, die, encapsulate it, and in this embodiment, very flexible device that can be mounted in along with other sensors to be worn, or as Jean-Charles was mentioning, for a variety of rather critical implantable types devices. And I know they work a lot in this area, and that information will be very useful for us. Christine talked about medical wearables and textiles integration, not only to work together with sensors that may be worn in other places, but also for stimulation or for treatments, as in the use of light, and besides being active support. So medical wearables used in this approach has a multi-phase. Eric, also from Fraunhofer, presented, Christine gave a hint to this at this conference today, about really a remarkable device, very thin, 100 micron thin, with embedded actives, flip chips, a battery, and a wireless interface, and something that's extremely thin. Certainly great progress in a technology like this, using ultra-thin embedded chips that are 15 microns in thickness. Something we should look at carefully. In fact, our colleagues at Fraunhofer, as they always do, have done their homework. They've offered all of these thoughts that they put in when they think about designing medical wearable type devices: choice of substrates, integrated power, communication, multiple sensors, all this kind of stuff. Very, very important. So our roadmap is primarily, again, focusing on wearables as is, but we're trying to diversify it. We focus on the standard physiological parameters, however, in medical grade, so high fidelity electronics. Communications are critical and important because the data can't be compromised when it's communicated. And of course, energy management is always important. Nobody wants the battery bigger than the device. Quite opposite. So together with the work we've done with GE, sponsored and by FlexTech, Semi, and NextFlex, we've been looking at this progression of systems, and as pointed out, already mentioned about the vital patch, the interstitial fluid system and the sweat hydration patch are examples of systems that take in fluid, perform analysis, and report the information out. Clearly, these types of devices are things that need more work, more development, but clearly have a great opportunity for improvement of one's health and improvement of one's healthcare. So our roadmap looks at various factors. In some sense, if you look at medical wearables, you have to look at materials, you have to look at packaging, and of course, the diversity of the devices themselves. Just materials alone, point to the need for substrates that are more and more stretchable. And for that matter, as we heard from Joey Mead this morning also, if you want to have a stretchable substrate, you have to have a suitably stretchable ink. Luckily, there are such materials available commercially, and we've been working with some of those, but they need to get better and better. And of course, without going into all the details on this chart, materials like those from liquid wire or similar material from the Air Force and maybe soon from UES provide a great opportunity to work with highly stretchable metal gels, which basically have very, very low resistance and are very tolerant of high fatigue cycles and high strains and many, many cycles over and over. As pointed out, we're talking here about a fraction of an ohm of resistance. And so the projects also focus on the packaging and the fact that a medical wearable device of the kind we mentioned needs to consider all these facets. I mean, this is the entire package. Obviously, the thin die or dies is critical in the various components, resistors or sensors, capacitors that will be printed on, and the various communications all need to be taken care of. And of course, with that comes a need to study from design and modeling, simulation, choice of materials, printing strategies, integration, assembly, testing. All that needs to be considered very carefully. Our vision is that the die will be modest in their function. It won't be overly complicated. However, as the roadmap continues, they will become more complicated. They'll typically be single layer, but multi-layer will be in sight. And of course, the die will be thin, components will be thinner and placed on these substrates using some form of robust interconnection. Robust interconnections could include the material technology that's offered by a sunray technology, which is using a magnetically aligned metal particles in a resin, which can vary in modulus and be tuned to the specific application. Device assembly and packaging will be critical, and the use of equipment that will handle thin die and thin substrates will be key. And of course, nobody wants to do this piece by piece. It will all eventually have to go toward manufacturing. So I won't go over the details of the packaging, but clearly the eventual need for multi-layer flex circuits that are thin and light and easily worn or incorporated in such devices that could be as part of a garment that you wear. And very similar to what NextFlex was showing on their tables will be some of the future requirements needed. And of course, ultimately, we'll need higher volume and lower cost. We do know there are things that are needed. In fact, you don't normally buy unpackaged die. An unpackaging die is a good way to destroy them. So this is something that industry will eventually maybe recognize if there's a need, but the need for unpackaged die will be certainly very important, as well as compliant interconnects, use of appropriate substrates, and all the rest of things that are important for this, including ultimately encapsulation suitable for the application. So wearable devices are going to cover electrophysiological, motion, strain, and posture, worker safety and productivity. And of course, as we mentioned, they'll become finally the smart bandage that we dreamed about when we started the CAM Center here. And we're talking to our colleagues at that time, the United States Display Consortium. Everybody was drawing pictures of smart bandages. I think the smart bandage is 10, 15 years after is still not there, but it's a lot more in reach than it was. Especially as we start to look at microfluidics, analyze, do better wound care. In addition, we may even be able to provide prescription drugs and of course sense them and whether they're doing what they're supposed to do so that people don't have to go to the doctors. We are in the process of revising the roadmap, and we welcome input from all of you, academic and industry, government as well. But in particular, those from the medical device industry, which I don't believe we have any members. In particular, we look at revising it based on reviews we've got to look at current future technologies, product packaging requirements and challenges, identifying specific drivers and unmet medical needs, adding a section on implantable medical devices that include pacemaker, but other types of systems as well. Also brought up in review was regulatory requirements, medical device and human tissue interactions, and device safety, even a statement about the broad impact of COVID and how now we have a much more realization of the benefit of having these devices. And will that make them happen faster? As well as electronics, miniaturization, and sections on power, wireless communication, and new systems, operating systems that might be needed. And so with that, I'd like to thank everybody who's contributed, and thank you for your attention.
So while he's setting that up, I want to thank you for attending and thank you for inviting me to talk this afternoon. I am the co-chair while Bill is the chair of this chapter on single and multi-chip integration package. And I should say Bill is the champion of this chapter and actually the champion of the entire roadmap. I just want to give you a little background about myself. I was recently transplanted to Rochester in New York, not far from here. Most of you know me from Promex, but I did a reverse migration and moved to Rochester. So let me give you a plug about Ames Photonic. We are NanoFab at Albany here, and myself, I'm in the test assembly and packaging facility in Rochester. So we do a lot of packaging there. About our chapter, which is chapter number 8, a total of 23 chapters, and you've heard speakers from previous other chapters like Mark, chapter 4, but I will be talking about chapter 8. Our roadmap is downloadable, as some of the other speakers have talked about, and we are very pleased that our roadmap was cited by DARPA in their latest funding opportunity announcement for next generation microelectronics manufacturing. So, I mean, our roadmap is quite important document out there. So my chapter, I'll be talking about some of the requirements of single and multi-chip package and some of the manufacturing aspects of the package. The manufacturing aspects I'll be talking about is wafer singulation and thinning, some wire bond innovations, flip chip, substrate, board assembly, and also additive manufacturing. Here are the contributors of the chapter. As you can see, there is a huge participation from the University of Binghamton right here with Benson, SB, Bhagat, Shrikant, and Scott, and I think we also have Eric Kotz from Binghamton. The electronics industry forecast is very bright, and this chart you've seen before. There is going to be a growth of 5.7% in the next 4 years. Most of the growth is coming from automotive at 12.9%, and also growth from the mil-aero sector. And the HPC cloud sector is quite high. The PC sector is slowing down. I think PC is falling behind because the growth has been very big in the past. The major market driving force for this growth is Internet of Things to Internet of Everything, smart mobile everywhere, data cloud, 5G, data centers, autonomous vehicles, wearables, and health, which you just heard, aerospace and defense, which you also just heard, and the demands for this market growth is for devices to perform better, compute faster, less power consumption, run cooler, all the things you've heard in the last 2 days, higher signal integrity, good power integrity, high bandwidth memory, low routing loss. And on top of all of this, they want low price, they want it to be reliable, they want it to be lightweight and smaller footprint. And you also heard there's also a requirement to go cleaner and healthier. So the solution for all the demand is for our HI parts to go to smaller nodes, which you've all heard about, to go taller, go 2D and 3D, and pushing for smaller and smaller interconnects, smaller line space, shorter distances, including going distance in the Z direction, going a shorter distance in the Z direction, which requires thin wafers, which I will talk about a little, and more TSVs, more use of bridges, and more use of embedded components, and also going co-packaged with optics. So here is a roadmap for single multi-chip roadmap metrics for some of the HPC, oops, go back. For some of the HPC nodes. Currently for HPC, the nodes for this year is 5 nanometers. year of production, which is actually quite true because AMD is using 5nm nodes in a commercial Ryzen product. And its roadmap is to go to 2nm in 4 years. So I won't go through everything, but here's another roadmap for number of pin counts. Currently, this year, it's at around 8,000 IOs, and they're planning to push to 11,200 in 4 years. Another metric is package dimension for high HPC packages. Currently, it's around a little over 3 inches, and they're pushing it to go to 4 by 4 inch, a whopping big package, which you can imagine the warpage would be a big concern. Another roadmap in the chapter is the flip chip geometries. So I won't go through everything, but I just point out the metrics for wafer to wafer, copper to copper interconnect right now is 2 microns. And it's planning to go to 1 micron in the at the end of the decade. For die to wafer, copper to copper interconnect is a bit bigger than the wafer to wafer. It's at 30 microns pitch right now, and it's supposed to go down to 20 in a few years. For the embedded die to substrate interconnect pitch, it's even bigger at 120 pitch, and they plan to halve it in about 4 years. So you could see there's a lot of aggressive miniaturization going on to meet the market demands. For warpage, this is a table from Benson. Currently, the warpage requirements for a mobile device of around 0.25 pitch. The warpage is around 110 microns, and they want to push it to 90 microns in about 5 years or so. So all of these requirements actually require a lot of new materials to be discovered, and also very aggressive push for process. One of the materials that can do this job of keeping warpage low for for big packages is the Ajinomoto built-up film, which you see here. This is taken from their website. And this film is the film of choice for all the HPC packages used by all the CPU manufacturers, all the GPU, CPU, GPU people use this film. And this, you could see the built up layers with the ABF film here. And in the ECTC paper this year, written by a team from Unimicron, they're even using the ABF film for RDL, and they can get much flatter geometries compared to their conventional film. So I would call this material a very strategic material. Unfortunately, there's only one manufacturer for it. This slide is from Kyo, who also gave a talk this morning, and it looks very familiar. There is a roadmap in here, which shows minimum bump pitch going down with the foreseeable future. It's coming down, the pitch is coming down, and in order to come down, we need better materials, higher resolution litho and laser processing, photoimageable dielectric materials that has to be, well, not low, and dielectrics to be lower than 3. And for speed to be increased, they need to look at smoother copper finishes. And for better power delivery, they need to look for more embedded passives and capacitors and thinner passives so that you could do more embedding. Okay, I'm going to switch to some chip level aspects of this talk. In a paper this year at ECTC, published by TSMC from Douglas Wu and his team, they mentioned that in order to be able to meet some of those requirements to build such fine pitch packages, they need to look at these are the challenges: chip size, chip thickness, process thermal budget, metal density, warpage control, dicing quality, surface treatment conditions, bond tool accuracy, and particle control. These are all very, very challenging parameters. And to be able to build these kind of features here, you need to be able to control all of these parameters. So I'm going to talk a little bit about chip size and also talk a little about dicing. This is how the foundries and the OSATs do their grinding of wafers. Wafers start out at 780 microns and they all have to grind it down. So these days people are going to extreme thin dies down to at the 5 micron thickness levels. To go to extreme thin dies, you have to rough grind the wafer and fine grind it, and then you also have to finish it to make it very, very smooth using CMP processes. Otherwise, your thin die will not survive. So extreme thin die, here's an example from IMAC, how they are able to achieve a 5 micron thin wafer. They actually take a wafer with TSV, they etch remove it, they bond it to a support wafer, and they flip it and remove the backside of this TSV wafer down to almost 5 microns, and they did some redistribution, bonded to another wafer, removed the support wafer to be able to get this extreme thin wafer of 5 micron TSV. So switching to dicing. Dicing is a process that's well established in the industry for ever since the industry started. Mechanical sawing is well established machines that disco sells. Recently, in the last decade or so, a laser has come on board, and then stealth laser also came on board. And now recently, plasma dicing is gaining market. I want to show you, this is a plasma dicer from AIM Photonics at Rochester. And we're able to do plasma dicing. The reason people like to do plasma dicing is for very small dies. It's a very efficient way. It's not very efficient using saw or laser for extremely small diodes. Another new way of singulation, which I'm copying this from Ron Koch. He allowed me to use this slide. This is a very interesting way of singulation by scalping the silicon off to remove the top epitaxial layer of the die. Oops. So these dies are very, very thin. I think they're in the 5 micron or less thickness range. So you can imagine this would be very useful for embedding into substrates. Here's a schematic of how they do it. They have to use MEMS process to to make this area below the die more etchable. Here is a slide from Ivy Jin, who is a contributor on the single and multi-chip chapter. She has a roadmap of the different wire bond material distribution. It looks like gold is going down as expected, and silver is just starting up and it's going to be picked up in a few years. Palladium copper wiring is going to pick up, I think mostly due to autonomous cars. Copper is also inching up. So I don't see a roadmap from her on the pitch of the wires. So I think maybe the wire pitch is not getting any smaller. I think this is almost towards the end. We also have a reliability table in the chapter. And as Bill mentioned, the reliability part is going to split off to a new chapter, but on the existing roadmap, it's still there. And you can see on a heterogeneous integrated package, how many things can go wrong. These are all the things that can go wrong in a package. And one of the more concerning things is electromigration. So electromigration is quite a concern because dual heating and hot spots due to thin layer exist and the higher current density of such fine features. So to mitigate this, people are using software and physics-based model to predict and mitigate some of these problems. I also want to point out that one of the ways to improve performance is to lower process temperature. So people are looking into bismuth solders, which have lower melting points, and they're looking at how it could be used in HI packages. So they're studying electromigration behavior. And I think this work is done at Binghamton. So I think I am wrapping up my talk, and I'm happy that you all stayed for my talk and haven't fallen asleep yet. So the summary is the mega monolithic silicon chip is giving way to mega packages, requiring mega integration of chiplets. The single and multi-chip integration chapter covers the building block technology based on heterogeneous integration from architecture and design to assembly and manufacturing. And I would like to invite you all to participate in the roadmap. You didn't know that this was a recruiting session, but it is a recruiting session from all the speakers that have open invitations for you to participate. With that, I would like to end and thank you very much for listening. And Bill, what's next? Thank you.
I'd like to suggest that we do a roundtable in the sense that I would like to invite all of our speakers, one chair, and you can invite you to ask us questions, opinions, objections, whatever, and I invite the speakers to ask each other questions, and of course, I will ask the first question. So, Shafi, do you want to come and take a chair? We are a low-cost operation. We pick up our own chairs right over there. So Benson, do you want to come and join this group here? So you heard me start off discussing the overall. We have 23 chapters. There's one extra chapter, which is the executive summary chapter. So then extra. And since we since we started in 2019, we released the first chapter, first edition. And when I go and look at it, the world is changing so fast. Much of what we have are different today. And particularly what I see today is that data science, artificial intelligence, machine learning is driving our industry, but also is we ourselves need to see how does data science, machine learning, artificial intelligence, how do we use it in our roadmap to see how our future of our profession is going to be either changed or consolidated or whatever with our roadmaps. So what I'd like to invite is to invite you to talk about what you think about artificial intelligence, data learning, but more, just as well important is the data science, the large amount of data that we have in our own profession. Who wants to start? Shafi, do you want to start from one side? You talked about collection of data, right?
Yeah, you volunteered me. Okay, so mostly about the machine language. I'll give some comments on the machine language. AI and data science is still a little nebulous right now in sensor domain. If you see my talk, I was talking a lot about intelligent edge processing, microprocessing. If you don't use intelligence or machine language at the edge itself, the amount of data that you need to transmit is just impossible. The bandwidth doesn't exist, or the power that it will require to transmit just doesn't exist. So in our world, in sensing world, I gave you the example of that water bottle, right? The architecture thinking is you add some machine learning language in the microprocessor at that level, at the firmware level, where you remove the noise, you reduce the data and transmit only the required signal. So that's where the machine language is very critical when it comes to how do you control and manage the data set right at the edge. Is it happening? Some of the applications, yes, but it's still not very widely used because of the power needs, because the architecture of the whole system is still not there. It's coming up, it's evolving. I have many applications. If you want to know, I can have some examples if you talk to me one-on-one. But yeah, from that perspective, machine language is very important.
So do you think we want to think about providing a collective data science in terms of establishing technical to help us to move that part forward?
From the sensor integration world, yes, that will be really helpful. We just have to figure out how to define the scope, so it becomes more of a executable and doable. Because right now, when we talk about AI, ML, and data science, it's still a very broad and wide field. The way you use machine language in the sensing world at Intelligent is different than what you use in the data science.
Oh, I'm a big user of AI using my smartphone. So I really like anything that can improve my life and make me smarter and do things faster. I use AI all the time to identify plants and bugs and things like that. So, so yeah, I think anything to improve AI is a good thing.
So let me clarify one thing. If any of you read the literature 20 years back, what AI was, to me, it's still all A and no I. Let's get this straight. Machine learning is a different beast. It's a tool that you use to process data, and it appears to be intelligent, but the kind of intelligence that we thought about 20, 30 years back is still not there. There's nothing good like our little thing we have inside our skull. So thinking of AI, it's not just AI that's producing data. We need AI to consume the data at the edge, yes, but we need to use intelligent processing technique to do a lot more, including how to design heterogeneously integrated system. If you're really thinking of system level design, the complexity of optimizing across the layers cannot be handled by any EDA tool that we know today. So this is why we need AI to design, to do smart design space exploration. So do not look at the design space exploratively, you can take a Monte Carlo approach and sample it, or you can use intelligent heuristics to fit into your tool to explore that space quickly. It comes in not only useful in the design of heterogeneously integrated system, but it's also very, very useful in designing new material, boutique materials that are needed for this. So material synthesis, designing package, coming up with solutions. It's all over the place. But AI is all A and no I to me. Machine learning is good.
Yeah, I was thinking in terms of the design process of the package. That's a great place where, because of the complexity of what we're trying to design and the amount of alternatives you could consider, tools that could simplify and optimize that would be a great application to be explored.
I'll go back to what Shafi said, because we both have common in sensors, and medical devices with sensors certainly need the same kind of approach, especially devices that are supposed to provide accurate diagnoses. Now, whether that decision-making is occurring on the patch or whether it's occurring on a mobile application, a mobile phone nearby, or the cloud, I don't know. But I think we read a lot today about all forms of medical diagnoses being improved by using artificial intelligence. After all, when a radiologist scans an image on the screen, do they really see everything, or do they need some guides, some more quantitative guides that look at the data, look at the image intensities, and make that decision for them? I think the same goes for the chemical analyses and all the other things as well. So it'll be very, very important. You have a person online.
We have John. Yeah. He did. So AI, I mean, it is, to me, if I look at designs, complicated situations where you have multiple devices, how do you route it, right? Anything that's going to make the routing easier is probably going to help. So our center actually uses AI for, doing more of the intercommunication between tools, processing tools, to help tools make decisions on how to make self-correction. Right, so that took a lot of work as far as, how do you provide the database of faults and relate it back to a change that you made, right? So I think that's really the main challenge is how do you feed enough data to these AI systems to make sure they understand how to make the decisions that's going to help, either optimizing a design or optimizing a process or whatever you want to use AI for. It's really the input that you're going to put, you give the system is what's going to drive the output. Right, you look at, I think there was an article about Tesla where they're building that supercomputer just to do visualization, understanding what the scenes are showing you, and then identifying things that may get in the way of the car or it's going to affect, how that car should be driving. Right, so they're putting a lot of effort into it, but really it's developing the system itself. John, you want to add to it?
Sure, absolutely. I'll comment on the sensors and edge. We have two different kinds of edge in the DOE experimental environment. The first is the high performance edge. So even though Moore's law has been tapering off for compute, or at least the Moore's law driven by transistor shrinks, we're still seeing sensors that are doubling in resolution each generation and also doubling in data rate. one of the cameras we have for cryo-electron microscopy generates data at a rate of 200,000 frames per second. And so moving that off of the sensor array is very challenging. But it turns out a lot of that data, the raw data is not meaningful. You only have regions of interest, and there's also a lot of signal processing that you can integrate together in the sensor. So that's a huge shift for us, is integrating intelligence into the high performance sensors. The second area is distributed environmental sensors. So for climate data, things like that, I think the word that they use in DOE is, or not word, the phrase they use in DOE is converting raw data into information, because information is a lot more compact than sending all the raw data and having it processed elsewhere. So they train a model on the sensor on the edge, and then they ship the weights of the model back. And that trained model is actually contains the information that you're looking for, rather than just processing all of the raw data. So definitely a huge area of growth is the edge and the data intensive computing. I'll also comment that we've seen our data rate used to be mostly outgoing from supercomputers, and now the amount of data that we have coming in from sensors is now exceeds the amount of data leaving the data center from simulation codes.
Kanad mentioned about using AI and machine learning to seek new materials, that we want to optimize. Would you like to comment on that? Because I understand your national lab has involvement in that.
Yeah, so that would be Kristen Person. So she leads the materials project. Materials project basically uses the supercomputers and first principles density functional theory codes to predict the properties of a material before we've actually synthesized it. And they've created a database of tens of thousands, maybe hundreds of thousands now materials characterized through simulation. And we can also do reruns if there's a particular physical characteristic that you're looking for to optimize. If you can articulate it in a way that we can extract that data from a first principles electronic structure calculation, then we can rerun the entire database and extract that parameter that you wish to optimize. And it could even be sifting, like multiple parameter optimization. But the materials project, our supercomputing center has had, on the order of 7,000 users. In a period of just 2 years, materials project has 10 times more users nationally than have accounts in our supercomputer to access it through the command line. So it's enormously powerful, and it's just broadening its scope each year. It started with batteries, but now it's for microelectronics materials, automating research for better ferroelectrics, things like that. But it'd be very interesting for packaging materials. You were talking about improving, finding a material that has compatible thermal expansion modulus. It could automate something like that, for example.
So in some ways, the reason why I asked the question is that during the session on the first day, we have a modeling and simulation expert from I forgot what company, and the modeling simulation, the work that he was doing, the AI and machine learning is still new to them. And I was thinking that would be a very important area for pre-competitive research in academia across our areas. So that's what I was thinking about. and start with design all the way to the product.
Yeah, they should definitely talk to Kristen and look at the materials project. We also have, through the Exascale Computing Project, developed a code for device scale first principle simulation using adaptive mesh refinement that can scale up on exascale systems. So whereas device TCAD these days tends to be single workstation type things, this we could do detailed modeling of device, including electromagnetics, ferromagnetic, and electromigration, and can do it at full device scale. And rather than a curve fitting, it's really first principles physical modeling, which would be too expensive to do in a workstation.
Well, I did want to make one comment about the AI and the machine learning. We have to also think about the workforce and what the glitz we need to be able to track people. And right now, a lot of the universities are moving to have even degrees in machine learning. And there's one university that has a degree in artificial intelligence. So I think it's very critical for us to look at this not only as a means for us to be able to accomplish our packaging, but also as an entire paradigm. Because when the young people now coming through school look completely different. It's like a few years ago, it's 3D printing. People are starting in high school with 3D printing. It's a whole concept. Before that, it was very difficult for students to actually, conceptualize in 3D. Now everybody conceptualizes 3D. Now it's going to be machine learning. Machine learning is, hey, throw a bunch of data at it, let it figure it out, and then come back and tell me what it wants to do. So I think they're whole different, cutting a what if type of approach on things is going to be a whole different way of thinking. And I think we want to think along those lines.
Thank you. I think that's extremely important. Thank you for that very important comment. So Christine's sitting in all the way back. She comes from the Fraunhofer Institute in Berlin. So are they work ongoing at Fraunhofer on applying AI and machine learning, data science to the research work at Fraunhofer? Do you want to come down?
Unfortunately, I think we have not made that step yet. So of course we are aware of artificial intelligence, and I agree that there's not a lot of that around yet. It's machine learning, but we haven't really activities to include that in our packaging strategy, I think. But I know we're a bit slow in that, but we will have to do that in the future. But no, not yet. And one reason is that we are really concentrating on hardware, so we don't have these students yet which have these degrees in machine learning and AI. We're waiting for that. Yes. Yes, but it's electrical engineering, and there's not a lot of machine learning there yet. I think there's really more in the US than we see in Europe until now. It's changing because there's a lot of funding for AI. It's always called AI, but it has not found its way in the universities too much for, yeah.
So do we have questions you want to ask each other? The group here. I have questions from other questions, comments from the audience.
I'm Mark Schott from Binghamton University. I've heard kind of two sides here when it comes to automation. I mean, when we filled out our NIST question, I was all for automation because I thought that we needed to do it to reduce costs in manufacturing, to reduce development times for new products, in order to be globally competitive, right? I mean, we're competing against a lot of fabricators elsewhere in the world that their costs are lower than ours. So would you look, and then I've heard the other side where someone commented today that the development of technology is going to just drive more and more jobs in the industry, right? So what are we looking at when we look at machine learning capability, AI applied in that? Is that something that you feel we need to do to try and reduce the number of people that are involved in manufacturing type jobs, can make development of new products occur faster with, you know, maybe a little bit smarter, take a little of the workload off? You think it will be a beneficial thing? I don't think in development and research we're ever going to get rid of this, right? Just like you said, Kanad. But I think they're tools that could potentially be valuable tools. And I'm wondering how valuable you think those really are in terms of being globally competitive.
Well, I guess
I think the okay. I think the work ongoing at the let's see, assembly lab. What is the Benson? What is the lab? What is someplace lab called?
The smart electronics manufacturing line.
Smart. That's right. And in that one, what he stated is to understand how he can improve yield, how he can understand defects. And so by collecting data, understanding the sources of the data, by collecting data and understanding the sources, then he can understand where the defect comes from. Then he can understand how he can address the equipment and the materials. No, but that's different because you start from there, then you can go to the LiDAR factories. Yes. So at our single or multi-chip integration center, so last week, Chen, who is the between the samples that are always set, forwarding step. So when you set up one pipeline and then you apply the same thing, when you set up one wire bond machine and you apply that to other machines, you don't know that they are always the same. It's just the same way that we go out and buy a car and the car manufacturer salesman come on and said, all this car are the same. No, all this car are all within the spec. And so now if you have a way so that you can collect data so that one person, you set up the parameters in one wire bonders, then you can apply artificial intelligence to make it so that all the wire bonding will be the same. That's one way to look at the data collection. That's how she presented to us. Understanding artificial intelligence in those wire bonding machines.
Right. And from the talk that she had, all the wire bonders that they're developing now have, you know, standard vision, but it's more enhanced. It's actually looking at, in addition to just location, right? The ball locations, what features are happening. What he can actually, what they've done is they've actually looked at usage of the software. And as you increase the level of, you know, adjustments, automation, you're actually driving down the cost, but you're also making it more uniform. The products going out are more uniform. And that's what you're trying for. Yeah.
No, you just collect data.
Yeah.
Just collect data and analyze the data. That's what it is. I don't think about it as being competitive. I think about it as being doing our work more thoroughly. Yes.
Yeah, and having worked in automation at one time, I mean, yeah, automation to a certain extent is going to take away jobs, but also allows you to build stuff that you cannot build by hand. And that's really where I would say you're going with AI and applying it, is getting to those solutions that are not obvious, that you're not going to get to, that an engineer sitting in his Excel spreadsheet for hours and hours and hours isn't going to get to. So it's how do we get to those solutions so that the engineer who's sitting there using his mind, he's going to start thinking about, okay, if this is giving me the solution, why am I getting that solution? That's where explainable AI or things like that. How do I fundamentally, how am I getting there? What's that telling me that I didn't know before, that wasn't obvious to me? But how do I get to a solution that I was just never going to get to otherwise, whether it's something that's going to drive down my yield or give me a design in you know, over the weekend that I maybe would have taken me months to get to something that wasn't even as good just by brute force, having somebody sitting there doing it. I think that's where the opportunities are, is how does that drive us to something with the people that we have. And in some cases, it's a skilled magnifier. I don't have enough people to go do a certain design task, but if I have ways to automate and improve on some of that stuff, I can use the people I have to do those tasks that otherwise I'm just not going to get done.
That's similar to similar observation. DOE, there's AI helps people have the time to do tasks that would otherwise not be done. It's not something that we intend as a tool to get rid of people.
So John, you and I both watched the video from at the Hot Tub conference, the speaker from Tesla, and he has a unique perspective on how AI contribute to the development of computing, both software and hardware. And I thought that Tesla, in that sense, is very different from all the other car companies in developing the concept of training and artificial intelligence and training. And they built supercomputer for themselves. Okay, so okay.
That's the way you pose the question. Automation affecting either cost or job, right? I think it's a perspective, and the context matters a lot. If you heard about Amazon Robotics, right? Have you heard about Amazon Robotics? If you look at Amazon Robotics, they actually make robots for their own warehouses. Amazon actually employs more people in warehouse than robotics, but robotics do actually more work than people. So if you think about it, what Amazon does, again, is context and how the economy and how it impacts their business model, how they do the pricing model. They have reduced prices, right, for delivery. What they have done is they have automated the repetitive process of picking the stuff out and shipping it out. But in the process of doing that, what they have done is, it's called innovation, business model innovation. They have expanded. They have made this whole delivery process, the logistic process, even bigger and bigger and bigger, which requires more and more people. If they didn't have this Amazon Robotics in the warehouses, those people who were deployed or reskilled or retooled for expanding would have been still stuck in the warehouses taking out stuff from the shelf. So it's just a perspective and the context you use it.
To make some comments. Being an old man, I'm opinionated. So I think the solution is to really build it better. I'm not making a political statement when I say that. We cannot ever think of it any time so that we'll build 100% of the chips in this country. That's not possible for any number of reasons. You do not want the pollution. You want to preserve the water quality, conserve the water. Some things should be done overseas. It's taken for granted. But what we really need to do to be productive and to do things is to innovate on the technology side. And AI gives us a way of doing it. Very definitely, machine learning techniques. How to do things better, how to automate the boring test diagnostic process, how to refine the process. AI plays a significant role there. So again, I think the mantra is to build it better and maintain the leadership and develop the methodologies.
So it's also worth mentioning the guy, Neil Thompson, the economist I was talking about. The other part of his work has been tracking the relationship between advances in computing technology and improved worker productivity. The productivity index for a country really is a great indicator of wealth and advancement. And, you know, rather than, again, getting rid of workers and making things more cost effective, really the computers have improved productivity of individuals. And I don't see that it would be any different with the AI. Improved worker productivity lifts the whole economy. It's not a means of getting rid of people.
Take the chips, right? Take about 20 years ago, we didn't make a trillion chips. Now we're actually making more than a trillion chips. So our pie has grown. The reason it has grown is the productivity has increased. We have more people retooling their skill sets.
Going to see you next year. You'll be getting an email for a link to download the presentation. Hopefully we get them.